this year I have 3 students in a row, so I thought, well, 3 is the charm, right? So here's Ryan Leuze. Ryan actually started working on the project 2 summers ago. He did this for a couple months, and then he decided to come back this semester to continue the work. I definitely can tell the difference between now and 2 years ago. So 2 years ago, he was like, okay, I'll do whatever you say. So this semester, really, he's been doing a lot of readings, you know. So we've had a long discussion. Sometimes I feel like, hey, it's been like 2 hours. Should we really continue to talk, or should we really go to the lab and do something? So that really just tells you his passion, and for that I really appreciate it. So he spent hours and hours, really every week, trying to really, you know, follow Shane's footsteps, because his project is kind of similar to these nanopores you've been seeing. And again, for people who don't know how small 1 nanometer is, imagine you're cutting your hair into 5,000 equal parts. That's how small these nanotubes are. And you may also have heard of something called carbon nanotubes. So this is something very similar to what people have been doing in that field. So let's welcome Ryan.
Well, thank you all for coming today. I'm going to talk about the fabrication and characterization of these titanium nanotubes. And it's all the work I've been doing, obviously, with Dr. Shi right here. So, in the next about 12 minutes, I'm going to talk to you guys about some of the importance of titanium nanotubes. I'll talk to you about the methods I use to make them, the goals we have. I'm going to show you all some results. I'm going to talk about some discussion about those results and work into the future, and I'll give some acknowledgments. So getting into it, the properties of these titanium nanotubes are very important, and they lead right into the applications of them. So as Dr. Shi just mentioned, you can use many different metals to make nanotubes. But titanium is really the metal that is very strong, light, and also inexpensive. So it's a good candidate. Also, when you're making these nanotubes, you're forming an oxide layer on the surface, which is known as titanium oxide. And this is a semiconducting material, which also leads into their applications. So here I have a picture of these nanotubes right here. And as Dr. Shi pointed out, they're very, very, very small. If you can imagine it, one of these tubes is about 500 times thinner than human hair. So by putting these tubes all over the surface, we're drastically increasing the surface area to volume ratio. So some of these applications I've been talking about will be use in solar cell devices, use in water filtration, and use for detection of harmful gas. So we actually hope in the future to make a prototype so that we can detect hydrogen gas in a room. So our goal before we make that prototype device is to first make these titanium nanotubes highly organized. And by that, I mean this picture on the bottom right here. You can see this hexagonal structure. That's an example of high symmetry in the structure, which is going to lead to organization and more nanotubes per square inch. So our goal is to develop a reproducible way of creating something down here. And when I came into this work 2 summers ago, this is about where we were at. So we had quite a ways. So some of my methods that I use have to do with preparing the titanium. It comes to me in the sheet. It's 95% pure. I polish it down with using a polishing paper and just sitting there with my hand. Then I electro polish it to get to a surface that we can reproduce constantly. And then next I anodize it, which is the process through which we build the nanotubes. So we use multiple different solutions for this. We use a monosodium solution, this NaH2PO4, and we also have used an ethylene glycol solution, which I'll talk about in the end. So to characterize and to look at these nanotubes, we use the scanning electron microscope, like Shane briefly talked about, and we also use a little bit of an atomic force microscope, which is an AFM. So the scanning electron microscope really works by propelling an electron beam towards the surface of my sample, and it produces really nice high-resolution images that can be magnified over 150,000 times. So really, it's key to this research. And it's really a tool that's not hard to learn how to use, but it is difficult to master, and there's a big learning curve to it. So it does take time for us to image these samples when we're done. So the next microscope we use is the atomic force microscope. This is more like a physical device with a needle that's going back and forth across our surface to give us a map. And so with the program, we're able to build three-dimensional maps here to give us an idea of what our surfaces look like. So on the top there is a mechanically polished substrate, and on the bottom is an image of what it looks like after I've done my electro polishing. So let's talk about both those processes real quick. On the top are two images of the mechanical polishing. And so this is a process that takes me about 6 to 8 hours. I really sit there and shine the metal until I have a nice reflection on both sides. Then as I knead the metal, I'll cut it up into 2 by 2 square centimeters, as Shane talked about, and I do my electro polishing. So this is an electrochemical process where I'm using a butanol solution and running a voltage for about 2.5 minutes to produce these images down below. So if you can't see all the way in the back, there are some defects on these images down here, but we believe that in between the defects, there's more than enough room to grow these nanotubes. So here's some results from the AFM. This is like a numerical analysis. It gives us a measurement of surface roughness. So this second number right here is in the low hundreds, it's 105. That's the average roughness of the mechanically polished surface. And on the next slide, we have the average roughness for the electrically polished surface. It's at 7.3. So comparing 105 to 7, it's a big difference. So this electro polishing is really something we believe in. So moving on to the process through which we build the nanotubes. This is the anodization. It works by following this little circuit here. We use the titanium as the anode in this circuit. We put an electrolyte exposed to a small portion of its surface. And we use platinum as the cathode, the ground, to bring the circuit around. And so we apply 20 volts through here when we do our monosodium anodizations. And this image here is our setup in the fridge. Here's our cell with the titanium in it. Above is the platinum piece. And we attach the positive end right here. So as I said, we've done 2 solutions, a monosodium solution and ethylene glycol. So here's some images from the SEM, some results from extending our anodization time from 2 hours to 10, 12, and then 14. So these results indicate to us that by extending the time of anodization, we are allowing these nanotubes to be more self-organized. So up here we have our 2-hour image. These tubes have been grown in kind of a random order. When you compare them to this 10 and 12-hour image, there's definitely a lot more order going on here in these diagonal and horizontal directions. As well, the 14 image looks really good, but I think the 10 and 12 really take the cake there. So the next method that we've tried to use is this multi-step method that, again, Shane talked about a little bit here. We start with an electrically polished titanium substrate, and we do our first anodization. This image is a little saturated, but the idea is that this first anodization is going to grow the tubes in kind of a random order. And so if we can remove that layer of oxide, we can leave the imprints that the nanotubes have made on the surface of the titanium. This should be the most organized part of the nanotubes. So by leaving this on the surface, we know that we can preserve that order through a second anodization. And so right here, if you can see in this image, we have this idea that we can grow these nanotubes straight up. So here are my results up here. This first image is after the first anodization. You can see these nanotubes don't really have any particular direction. And this second image is of our oxidation removal. So that's the process that took us a very, very, very long time, this research. It really was looking for a chemical that's going to harm or remove titanium oxide without harming at all titanium. So you can understand the difficulty in finding a chemical to do that. So we came up with a sulfuric acid that's going to do this. And you can see in this image that it's not perfect. So we need to perfect the timing of this process. But after our second anodization, take this sample. We need to look at it in the SEM. I said, yes, we do. That's a great idea. Because maybe we just we did the whole oxidation with air. It was perfectly easy. And so I took my old sample, I took his sample, went down to the microscope with him, and we found that we had made this beautiful order here. So you can see the symmetry really well in these samples. And this is a nice zoomed out image. So this is really the first time we were able to do something like this. So we thought that's great. So we decided, okay, we want this layer to stick, so let's do an extended second anodization overnight for about 15 hours. Maybe that'll make something thick enough to really stick to the surface. So we ran this, got the sample, and I rinsed it off, blew it with air, and the entire thing blew off. Okay, well, still close. So that one looked good too. And I had some discussion with Dr. Shi, and we decided, okay, let's go back to the old solution. Let's use the solution that we know can form a solid layer, and let's build that on top of this. So then I tried that, and it completely didn't work at all. It just looked how it used to look, just awful. So we decided that we need to talk about what parameter do we need to have the same between these two solutions. Should it be the diameter of the pores, or should it be the distance between their centers? And we really concluded that it needs to be the distance between their centers should be the same, so that we can do a second anodization that will preserve the order. And so here is some results that I took where I was measuring the diameters of these tubes. This is my ethylene glycol sample. So these diameters look to be about 300 nanometers. Sorry, not diameters, the inner pore distances. And then moving on to the monosodium solution, these diameters were all within 150 to 100. So we really need to do work now in the future to determine what about making these tubes leads to their different inner pore distances. And if we can find that out, then we can set them the same between the two solutions and build a nice, preserve this array throughout a long, tall layer and really conclude our research. So the summary, a little bit what we talked about. We were able, and 2 summers ago, to make a nice reproducible method for electro polishing these samples. We have been able recently to make nicely organized nanotubes. We have achieved our goal of removing the oxide with the sulfuric acid. It goes back to the monosodium solution now. And yeah, our future work now is really to do the multi-step anodization using these 2 different solutions by balancing their parameters. And so, thank you, Dr. Shi, for leading me on this research. He is always there when I need him, and he is incredibly helpful. Thank you to Steve Anderson, as I'm sure everyone's going to say today. He is always there to help you. He is great with the microscope. He has taught me so much. And thank you to the Corette Scholars Foundation for helping me do this research, for funding it. It's all great.
Questions for our third speaker today?